So just to review here, calculations involving the strengths of acids and bases. We can do the percent ionization or dissociation, and this is used to express how much an acid or a base ionizes or dissociates. So it's the amount of H plus over the initial amount of acid times 100%. For a weak base, it would be the amount of hydroxide over the initial amount or the initial concentration of your base. So that's initial times 100%. Acid dissociation constant Ka, strong acids, Ka is very large. We don't write out the K expression. The more an acid ionizes, the larger the Ka value. So your Ka will include all of your AQs. So in this case, hydrogen ion or the hydronium ion, the conjugate base, and the concentration of the initial acid. So now let's do an example. Formic acid. This is methanoic acid. It's a monoprotic acid with a concentration of 0.10 mole per liter or 0.1 molar solution. If the pH is 2.38, what's the percent ionization and the Ka value? Methanoic acid, so contains one carbon. So this is your carboxylic acids. And you can write it out like this, or we write acids, carboxylic acids, a similar way than other acids, and that first H is the acidic hydrogen, which is that hydrogen. And then we have the rest of our ions. Okay, so methanoic acid is monoprotic acid, so let's write out our equation. We know that in water, it will be in equilibrium with its ions. So we're going to form the hydronium ion and methanoate will be what is left. So the pH is 2.38, so that means we have the concentration of our hydronium ion. So 10 to the negative 2.38 is going to give us the hydronium ion. So this is 4.17 times 10 to the negative 3 mole per liter. Two significant digits, 4.2 times 10 to the negative 3 mole per liter, because there's 2 decimal places in our pH. So now we know our hydrogen ion concentration at equilibrium. So we can put this into our equation. 4.2 times 10 to the negative 3. Our initial concentration and we get about 4.2% ionization. So not very much at all. So this is a weak acid. So setting up our Ka expression, we would have hydronium ion times your conjugate base all over your acid. So in order to solve for our Ka, we're going to need some information. Yep, we're going to need an ice table. Okay, so an ice table. Initially, we had 0.1 mole per liter solution, and initially you have 0 products. Now we don't have to include water here because it stays constant. So the change, this will be minus x, this will be plus x, this will be plus x. So initially 0.1 minus x, x, and x. And we can substitute these into our Ka, except we need to know what x is in order to solve our Ka. If we have Ka, we can solve for x. But we do know our x value because we found our hydronium ion concentration in the previous question when we calculated our hydrogen ion concentration from the pH for the percent ionization. So x was equal to 4.2 times 10 to the negative 3 moles per liter. So now we can substitute that value in to solve for our Ka. So 4.2 times 10 to the negative 3. So this is also 4.2 times 10 to the negative 3 all over 0.1. 4.2 times 10 to the negative 3. So now plug these values into your calculator and you will have your Ka value. So the Ka value for methanoic acid would be 1.8 times 10 to the negative 4. So you can solve your Ka value if you have a pH or a hydronium ion concentration. Okay, what is the pH of a solution of 0.75 molar acetic acid solution? Okay, so we need to find pH, which means we need to find hydronium ion concentration. Acetic acid is HC2H3O2 and we can do formal or informal. Produces the hydronium ion and the acetate ion. Okay. We're trying to find pH, so we need to find hydronium ion concentration. So again, you're going to set up an ice table. Initially, we have 0.75 moles per liter of our acid. We don't have any product yet. It goes through a change. And then at equilibrium, we have 0.75 minus x. We have x and we have x. So your E line, your equilibrium line, is what goes into your Ka expression. So Ka is equal to, and always set it up properly first before you substitute in your values. So hydronium, the conjugate base, all over your weak acid. You have a table in your textbook, any textbook, of Ka values. The Ka value for acetic acid is 1.8 times 10 to the negative 5. So now we can solve for x. So this is going to be equal to x times x over 0.1 minus x. So x squared over 0.1 minus x is equal to 1.8 times 10 to the negative 5. Now, remember, you're a chemist. You're efficient. So if we say 0.1 over our Ka value, if this number is much larger than 1,000, so we're going to use our 1,000 rule again. So if the initial concentration of our acid divided this time by our Ka value, if this is much greater than 1,000, we can assume that 0.1 minus x is approximately 0.1, which will make our calculations a lot simpler. So 0.1 divided by 1.8 to the negative 5 is 5,555.5 repeated. So this assumption holds, that's greater than 1,000, so for that reason, it's greater than 1,000, so 0.1 minus x is approximately 0.1. That simplifies our life so much better. So now we have x squared over 0.1 is equal to 1.8 times 10 to the negative 5. So 0.1 times 1.8 times 10 to the negative 5 is equal to x squared. Just take the square root of both sides. So 1.8 times 10 to the negative 6 square root. Just going to resize this. Okay, so now I know my x is going to be equal to 1.3 times 10 to the negative 3 mole per liter, and this is equal to H3O plus. So pH is negative log of H3O plus. So the pH is 2.87. So the pH of a 0.75 mole per liter acetic acid solution is 2.87. So when you have a question like this, write out your chemical equation, set up your ice table, set up your K expression, put your values in your table, solve for x, and then take the negative log of that number. So there you have it, some calculations involving weak acids.